talking about nematic shape equations.
All right, good morning, everybody. And yeah, today, so this lecture has two parts. One part today I talk about deriving equations on nematic shape equations, and then on Thursday I talk another hour and a half. I'm going to have to drink a lot of coffee to talk so much, but so I do applications on Thursday. So today we're talking about liquid crystals. So these are mesophases that exist sandwiched in temperature or concentration ranges between fully ordered crystal systems that has positional and orientational order, and liquids that have no position, no orientational order. So if you think about a crystal, you inject thermal energy, and then what you melt first are positional order degrees of freedom. If you melt 1 degree of positional order, you can find columnar phases. These are orientationally ordered systems with two-dimensional fluids, two-dimensional order. When you melt 2 degrees of positional order, you get layer phases, smectic phases that have orientational order. So these smectics, they on this direction act as solids, on the perpendicular direction act as liquids. If you inject more thermal energy, now you can melt all remaining positional order, and you find an orientationally ordered system. So here we have the nematic phase that have orientational order and positional disorder, and many biological liquid crystals have a superposed chirality, or you can put these low molecular weight liquid crystals, you put a chiral dopant, and you find a cholesteric phase. So this phase on a larger scale has a layer structure like a smectic, and on a shorter length scale behaves like a nematic. So you can discuss these kind of systems in terms of order parameters, positional and orientational order parameters, and then corresponding to this symmetry breaking transitions and symmetries, you can discuss them in terms of mechanical properties. So we go from anisotropic elastic and isotropic viscoelastic systems to just simple viscous materials. So this is then another view, more applied view. So liquid crystals are self-organizing soft matter in terms of constituent particles or molecules. We can find these liquid crystals in terms of rods, disks, and amphiphiles. So typically they are divided into 4 types. Here we have thermotropic liquid crystals. Here we have lyotropic. These are driven by concentration changes. Here we have polymeric liquid crystals. And here we have biological liquid crystals. So in terms of low molar mass thermotropic liquid crystals, as I said, we can have smectic phases, columnar phases, and nematics. They can be rod-like or discotics. And the interest in these kind of systems is that are self-organizing, and they are both structural precursors for fibers, for example, and as well as functional materials. So they are multifunctional materials. That means they respond to a variety of external fields, temperature, electromagnetic fields, etc., and interfaces, as I discuss in a minute. So here we have surfactant liquid crystals. They form the basis of surfactancy, soaps, detergents. So these are all lyotropic phases. We have lamellar, we have hexagonal phases, depending on temperature and concentration. And they're also used as templates for catalysis. So you can do fancy organic chemistry on these substrates. Down here, we show liquid crystal polymers. You can incorporate these rods or disks on polymer main chains. So these are high-performance fiber materials. You can incorporate them as a side chain using for ferroelectric, piezoelectric sensors and other display applications. And here we have liquid crystal elastomers, so we cross-link the polymer chains. So these are materials that are being developed for artificial skin and muscle. So you can also incorporate rods and discs in more supramolecular architectures, giving rise to liquid crystal dendrimers. These are, for example, widely used as rheology modifiers. So they're very sensitive to control. They can control viscosities. And over here we have the biological liquid crystals. So typically this is a big field. They can be divided into three types. One is frozen in liquid crystals, for example, bone, plant cell wall, eye, cornea. So in these kind of systems, the liquid crystallinity is frozen in. So it's a frozen liquid crystal. So we have in vitro liquid crystals. So you extract polysaccharides, cellulosics, polypeptides in solution. So these are in vitro liquid crystalline polymers. Or we can also have in vivo liquid crystals. So some people ask the question, why does nature uses liquid crystallinity? For example, spider silk secretions are liquid crystals. So here we have protein solutions that exhibit liquid crystallinity during the spinning of the spider silk. So those are examples of in vitro. Other examples obviously are biological membranes. So it's this embedded self-assembly, multifunctionality that form the basis of why nature uses liquid crystallinity. Okay, so now this talk is about interfaces. So a lot of people traditionally for the last 100 years have really looked at bulk behavior. Obviously, most applications depend strongly on surfaces, interfaces, etc. So boundaries. So obviously, liquid crystal displays are controlled by interfacial behavior. So this is an area that is evolving. Yeah, there is a lot of data out there, and there is previous work. I don't say there is nothing done on interfacial colloidal science of these liquid crystals, but still is not as developed as the bulk science. So this, I just quote some examples to give you a flavor. I think there is a lot of opportunity for math people sitting in this audience, and also for technological development. So we have new types of absorption orientation coupling. So if this is a liquid crystal water interface, that's a cyanobiphenyl, and if you load the interface with a surfactant, you can have orientation transitions from tangential to perpendicular. So this is absorption orientation couplings. So you can manipulate surface layers by absorption. We have very exciting shape actuation. Again, with using surfactant, you can do liquid crystal fiber to droplet transition by increasing surfactant concentration. Here we show creation of a topography which is decorated by topological defects that form a stable lattice of point defects, -1, +1. So you can decorate a free surface of a film with topological defects that are stable by just shining a few Tesla of magnetic field perpendicular to the film direction and creating these orientation distortions. There is applications in lubrication. Some people are pushing the idea that synovial fluids in the knee have liquid crystallinity. So if you have a substrate, a liquid crystal, there is a very interesting phenomena close to the interface. You can have layering and positional order that emerges close to the interface that enhance lubrication. This goes to the core of liquid crystals. These are biological membranes. So we have things like flexoelectricity, hard hard matter crystal systems, you have piezoelectricity. In soft matter, we have something softer modes. So these are called flexoelectricity. Things are easy to bend. So here we have a coupling between electric polarization and bending. So this kind of property, flexoelectricity, form the basis of the performance of, for example, outer hair cells that allows you to hear high-pitched sounds. So in the ear, you have two types of cells, inner hair cells and outer hair cells. Inner hair cells produce electric signals. Outer hair cells produce viscous pumping. So this thing can vibrate, right, and creates a pump, a fluid pump. And this fluid pump kind of overtakes all the dissipation that occurs in the ear so you can hear. So a lot of people are pursuing this line of flexoelectric sensor and actuators. So we have very exciting structural color in nature, besides pigmentation and chemistry, etc. So this is structural color. Is the basis of structural color in many biological systems is these chiral fibrous organizations. So fibers that organize in the exoskeleton, exocuticle of insects, for example, in a chiral format. The cholesteric system is a layered system in a longer scale. So they behave as Bragg, that gives rise to Bragg reflection. So it's this layering of these fibrous structures that are at the surface of beetles, for example, that gives rise to coloring, structural color. We also have new capillary instabilities. I talked about this point on Thursday. So for isotropic systems, you have Rayleigh instabilities, the conversion of fibers into drops to minimize the surface area. So a key point is for these systems, the surface energies are not only dependent on surface area, but on surface orientation. So orientation is a key variable besides the size of the object. So the orientation of the unit normal with respect to the fiber's orientation that forms the nematic phase. So you have new types of instabilities called Herring's instabilities that promote not the decay of a fiber into drops, but the transformation of a cylindrical fiber into a chiral object. We have new type of two-dimensional matter, soft matter. So we have liquid crystalline shells, very thin shells that can decorate nanoparticles or colloidal particles. And we have new type of foams, anisotropic foams. So this is, for example, mesophase pitch. So this is a carbon-based liquid crystal, viscotic nematic liquid crystal. These foams are very easy to form. You can boil this mesophase pitch at several hundred degrees Celsius. It's like boiling milk. If you put a pot of milk, you boil it, you're going to have foaming. So that foam forms very easily. Just turn on the heat, foam up, and it will cross-link and form a stable foam that form the basis of high-performance heat transfer. So you have an ultra-light object that is oriented. So nice properties. And now we have the emergence of new type of colloids, liquid crystal nanocolloids. So you can disperse using smart chemistry. You can disperse nanoparticles like gold nanoparticles, and you can immediately see that a sufficiently high concentration, when you drive these nanoparticles into a more ordered state, you can achieve new types of things like a nematic crystal state. So the nematic has orientational order and the nanoparticle has crystalline order. So you have two systems that are interpenetrating, one with orientational order, the other one with positional order. So but this kind of few examples, I just put it here to show that there is ample opportunity for new type of math. So the mathematics of anisotropic soft matter is virtually undeveloped. So there is a lot of stuff that we can do, and also for technical applications. So this is what I want to talk. I don't know how much I can cover. So I have another hour and a half on Thursday. So whatever I don't reach, I can shift onto Thursday. So we talked about order parameters. The order parameter is the Q tensor. We talked the associated free energies. We talked about the equations we can use for the bulk, the surface, and line, called nematostatics. Discuss a little bit the stress tensor. I always try to give some examples, physical examples of application of these stress tensors or manifestation of these stress tensors. Finally, talk about the shape equations. The key point in this field is there's always not only shape, but there is structure. So you have two things that come together, shape and structure. So you have to talk about stresses and forces, and you have to talk about orientational order parameters. So they come together and define a shape and a structure. And finally, talk a little bit about thermodynamics. So these are the order parameters we use. So we have an orientation distribution function, and the second moment is the order parameter we use, the Q tensor. So this is a typical orientation distribution function. This object, this order parameter that form the basis to describe these oriented materials, can be decomposed into two parts. One is the scalar part, which is the amount of orientation between the molecules and the so-called optic axis or average orientation. So this variable for thermotropics is a function of temperature. Here temperature increases, so this order parameter decreases, or also a function of concentration. So this is a nanoscale variable that is a fast, short length scale variable. The other component of this Q tensor is the optic axis. This is a slow variable that describes defects and lives on the micron scale. So this object contains long wavelength information, short wavelength information, slow process, and fast process. So the problem is multi-scale from the beginning. In addition, so if the plane perpendicular to the optic axis is anisotropic, for example, close to an interface, we have biaxiality, and this P is the biaxial order parameter that gives an indication of the bias on the plane perpendicular to P. We'll show some examples where this biaxial order parameter becomes important. So when we deal with interfaces and membranes, in addition to the orientational order parameter, we want to describe the shapes of things. So we have parabolic, hyperbolic, elliptic surfaces. So here the most convenient way to couple B and Q is the curvature tensor, which is minus the surface gradient of the unit normal. So this Q tensor can be decomposed into two parts, the average curvature H and the deviatory curvature. You can work with Gaussian curvature, of course, but this HD split for doing equations, doing calculations is very useful. And D just measure the deviation from spherical shape. D is 0, you have a sphere. When D deviates from 0, you know you start getting non-spherical shapes. So for some problems, for example, if you want to describe a system that is like a soft membrane with embedded fibers inside the membrane. So the fibers are described by a Q tensor, and the membrane elasticity is described by the curvature tensor. You put B and Q together. If you have other things like filaments, disclination lines or defect lines, contact lines, so in addition to have the Q tensor, we also incorporate the Frenet-Serre equations associated with this filament. And again, these filaments and contact lines can be decorated by rods, for example, and then we can couple Q, for example, with a tangent to the contact line. So this I show you next couple of examples, 3 examples of what happens with the Q tensor and how to look at canonical problems. If you have the Q tensor in canonical problems, like let's say you have disclination lines, you have interfaces, and you have disclination line on interfaces. So what do you see? So typically the way to represent, so when you do computer simulation, the best way is to solve your Q tensor equations, and then you add a unit matrix divided by 3, and you can visualize into an ellipsoid because the Q tensor has negative eigenvalues, so it's hard to visualize. So if you add I divided by 3, now you have a tensor that is easily visualizable. You can visualize it very nicely, and there are different approaches in the literature. Sometimes you want to represent it as a cuboid or as an ellipsoid, depends your problem at hand. So, but the Q tensor has 2 order parameters, S and P. This was the biaxial, this is the main order parameter. So it defines, for physical situations, this phase ordering angle. The vertical is P, the horizontal is S. So all the possible states of this nematic is contained in this ordering triangle. The edges of this triangle are purely biaxial states, as you would have a plane, a planar nematic. The center denotes the isotropic state. The blue lines here denotes the uniaxial state. Any other point in the interior is biaxial. So if you look at about critical points of your free energy or typical problems, let's say this is a monodomain nematic. In this case, it's a cholesteric, doesn't matter. So it lives very close or on this. A cholesteric is biaxial, but if you have a nematic, this point here is going to be right on this blue line. If you have an isotropic nematic transition, so we have a source, is isotropic, is at the center at this point where all these biaxial lines cross. So at this point, all the eigenvalues are 0. So here, this is a uniaxial root or a sink. The system is stable. So this is a source, the system is unstable. And then you have this important root here, which is a saddle of your free energy, which is a defect core. A defect core. This is a disclination. There are many types of disclination. I just read a paper yesterday. Somebody is able to produce disclinations of strength plus minus 10. So typically, normally, situations are, disclinations are quantized. The winding number of a disclination is quantized. So typically, it's mass plus or minus 1/2, plus or minus 1, etc. But this is a 1/2 disclination. So you can see that you have important connections. So here you have a sink saddle connection that describes topological defect. Here you have a sink source connection that describes, for example, an isotropic nematic interface. So getting used to this triangle, then you can tackle a lot of problems by just looking at this triangle. For example, if I have a nematic liquid crystal and I put a magnetic field or an extensional flow on this nematic, I know I'm going to move from here to this line. So I know if you want to do asymptotics, if you want to do order of magnitude calculations, you can do a lot of physics by just looking at trajectories on this plane before solving any equations. So now I show a couple of examples of typical conditions inside this plane. So these are disclinations in capillary. So in this talk, we're talking about confinement in drops, fibers. So this is a typical carbon fiber, nematic fiber. On the edges here, you have disclination lines. Anytime you insert a liquid crystal in a capillary confinement, if you have strong anchoring, for example, here, this is perpendicular orientation on this capillary, you're going to find two topological defects of strength plus 1/2 most of the time. I describe sometimes other, you have plus 1. So you're going to have two defects as indicated here. These exist on lines that run all along into the fiber. So as you move close to this disclination line, you go from a fully uniaxial phase into this disclination line. This disclination line core lives on this diagonal term. So this moving in space from here to here describe moving on the phase plane between a sink and a saddle in this direction. So in terms of eigenvalues, the signature of defects is the eigenvalue crossing. So here you have a uniaxial phase, so you have two equal eigenvalues, and this is the distinct eigenvalue, and as you get closer and closer, one of the eigenvalues peels off, and they cross at this. So at this point here, you have a uniaxial phase, that is, you are on this line here. This is the uniaxial line. So in fact, in this kind of problems, visualizing defects, detecting and visualizing is always going to be the big issue. There's still a lot of people trying to improve what we have. You don't know where this problem, defects are there, but in a dynamical problem, in a flow problem, you don't know where the defects pop out and where they annihilate. So it's always the big issue. So this is an important problem, these connections between sink and saddles. Many times, as indicated in this is a lyotropic, thermotropic called chromonic liquid crystal. This is experimental data of sunset yellow. So this colorant that is a food additive that is a liquid crystal. So yeah, liquid crystals, they're also in the food we eat. So when you fill your capillary with this chromonic liquid crystal, this is a cross section, you're going to find many times the emergence of these branch points. So here I have a +1 disclination. It branches off into 2 +1/2 disclinations following Kirchhoff laws. There is an interesting connection, the Kirchhoff law of branching. So yeah, they are obeyed by vortices, they are obeyed by electric wires, they are obeyed by liquid crystal disclinations. So at this branch point, it's interesting. Now you come this way on the blue trajectory, and you want to say, what do I see in this phase ordering triangle? So you started here in the +1 disclination, you started here, is a saddle, you go to the branch point, that the only solution to a branch point is an isotropic state, which is in the center. So you have a saddle, a source, and a sink. So this other example, what happens when you have phase transformations from an isotropic phase into a nematic phase. In this example is 5 CB obtained by quenching. You lower the temperature, so this phase is unstable. It converts into the nematic state by nucleation and growth of droplets. So now we have nematic droplets. Nematic droplets are different than other droplets because this is an ordered fluid. We have orientation in there. So what's new? There are many things are new, but some of them are just shown right here. So first of all, if you have a nucleation through an homogeneous nuclei and germ, this area here, you have tangential orientation. This area sector here, you have orientation that is perpendicular, called homeotropic orientation. So there is an orientation gradient along the interface. The net result is you have biaxial sectors and uniaxial sectors. In these sectors, the orientation is perpendicular to the interface. In this sector, the orientation is tangential to the interface. So why is that? Because in this region here, if you take the cross-sectional plane, if you have a director this way, the cross-sectional plane is isotropic. There is no bias. It's uniform because you only sampling a nematic phase. Here, if you take the plane perpendicular to the director, you're going to sampling isotropic states and nematic states. So the state is biaxial. So this is reflected too if you cross this interface in the horizontal direction here or in the vertical direction there, you're going to see a manifestation in terms of in the phase ordering triangle and in the eigenvalues. So here is biaxial, so you have 3 different eigenvalues, and you go from a sink into a source. Here, the isotropic phase here, this phase is unstable, it's a source. So you go from a sink into a source, but you go through biaxial states. Biaxial states. So you have 3 different eigenvalues. When you cross the interface in this direction, you go from a sink into a source, and it's always uniaxial. So you take this direct path that is totally uniaxial. So just a little drop. I talk about more drops later and on Thursday, but so you can see that a nematic drop is very different than any other drop, just the total physics is different. This is another manifestation of what's different. So here you have a nematic germ. Yeah, it's not circular, so it grows due to, in this particular case, differential growth speed. The speed of growth in a nematic depends on the orientation to the surface. So you might have slow and fast growth modes. So it leads to the formation of cusps. Typically, you know, there are many ideas, many connections between, for example, topological defects and other areas of physics. And the kind of canonical view is so-called Kibble mechanism, that topological defects, they form by the impingement of drops. You have 3 drops with different orientation, they come together and they form a disclination. That's the Kibble mechanism of defect nucleation, using from liquid crystals to cosmology. So here we found other defect forming mechanisms that has no impingement. This is single drop. So if you have a drop, it grows. I have a movie, but I'm sure I'm going to have problems, so I didn't put it on. But so we have droplet growth with differential speed. You have instability, cusp formation, and you can clearly see here the cusp formation forming at this point, and with the encircling, engulfing of an isotropic component that is then left behind. This surface is moving up, right? And this isotropic region is left behind, injected into the nematic phase, forming now a disclination or defect inside the nematic, as indicated here. So for this particular problem, this drop, we put the directors in the vertical direction. And you can see that as the drop forms, when the drop forms here, you have a tangential orientation. So in the beginning, everything was perpendicular. So if we go in the vertical direction, and everything was perpendicular, we just should see everything as uniaxial. But because now you have topological defects that are being nucleated and form at the interface with these kind of configurations, here you're going to have biaxiality. And so here we show the stages of the instability of the disclination emission from the interface. And this shows, for example, the eigenvalue profiles as a function of space when we transverse this interface in the vertical direction. So when we go along this direction. So in the early stages, when you are here, so these also are useful. These are the geometric corresponding figures to the eigenvalues. So in this early stage of the instability, you have a uniaxial sink source. So you move from this point to this point. Remember, here I have an anematic drop, and outside I have an isotropic state. So I move from a sink to a source in a direct way through a uniaxial path. As the defect forms, now defects, as I just showed you before, they form biaxial states. So I have a sink to a source going through biaxiality because the presence of a topological defect. And at some point I'm here is my disclination, my interface is here. So if I move through the disclination and through the interface, I'm going to have a sink saddle source path on this triangle. which describes then defect shedding from an interface.
Before you leave that slide,
Yes, sir.
so this is the result of a calculation, right?
Yeah, yeah.
So the light blue is isotropic, the dark blue is nematic.
Yeah, this is nematic. So this is isotropic.
The
These figures correspond to these three figures.
So the bright spot is there's no CD in it. It's just a drop.
This drop, the original drop, yeah, it's just a nematic drop that forms a germ that forms in an isotropic bath. You nucleate a seed in the bulk. It's homogeneous nucleation experiment.
No, I mean the calculation on the right-hand side there.
Yeah.
You eventually have a little drop that's sort of being trapped in the bulk.
Here,
Yeah, there's
Yeah.
nothing in the drop. It's just isotropic fluid, right?
in the drop is an isotropic state, yeah.
So this happens spontaneously.
This drop form at the interface. It's been invagination process. So it's like a biological process of invagination. So this isotropic area was engulfed by the nematic phase right here. And then this interface is moving up. And so it's shed, is emitted from the interface, and now finds itself in the nematic phase. And then further coarsening, it is a disclination line.
What causes this instability?
There are many different modes. One mode, I show you one example before.
What causes this?
Yeah. This is one, I give you a more complete picture. So depending on the type of liquid crystal and the type of quenching you do, this all with homogeneous cases. So here you always want to have this kind of heterogeneities across the interface. Here you have biaxial state, here you have uniaxial state. You cannot avoid that. So in this mode, we have 4 points. So this is an interesting kind of symmetry problem. Here you have biaxial, uniaxial. You have a strong, sharp gradient. So in that point, in this particular case, you're going to shed 4 drops. 4 disclination of strength minus 1/2. 4. This is for deep quench. Weaker quench, you can shed 2 minus 1/2 disclination. This particular case, the orientation is vertical. You have differential growth velocity. The growth velocity depends on direction of n. So you have area that grows faster than others. So this area here is slower, is falling behind. This whole thing is the growth is with time, is growing with time. You have slow region, fast region. The ones that fall behind form a kink, and this kink then forms a disclination. Now, free energies. So talk about a kind of generic type of free energies we use in this field for liquid crystal interface surfaces, etc., and also for surfactant-laden interface. And then I say a few words about the energy ratios and how you can do a lot of physics by just looking at key energy ratios before doing all more complete calculations. So the free energies for typical problems that have interfaces and contact lines have bulk contribution, a surface contribution, line contribution. So for the bulk, you have an ordering. So this is an expansion in the order parameter you can derive from molecular theory, etc. So this is the transition from isotropic to nematic. So a polynomial in the order parameter. The other 2 important components are the anchoring component and the gradient component. So here what we mean by anchoring is when you have an interface or a contact line, you can assume that there is some kind of preferred orientation close to these objects. And so then you say, how is this object described? An interface, a unit normal, disclination line, a unit tangent. So you have anchoring energies. So in addition to interfacial tension, isotropic interfacial tension, and line tension, we have anchoring components, and these anchoring components then coupled your Q tensor with your unit normal to the interface. In typical situation, you have three characteristic cases depending on temperature. You have planar anchoring, you have tilted anchoring, you have homeotropic anchoring. So typically you can move around this plane many times by changing temperature, for example, or adding surfactant. So there is more physical, more molecular explanation, but we leave it at this point here. For example, in this configuration, you prefer the rod-rod interaction. In this configuration, you preferring, there are entropic components, but you preferring the rod-substrate interaction. Likewise, at the contact line, many times, for example, you have azimuthal orientation on contact lines. And I know many times when you have line pinning, etc., you have hydrodynamics, etc., but many times you also have to include what is the effect. If you say this exists, that we all know exists, then simple calculation shows that anchoring effects propagate into a contact line, and therefore there are contact line torques. And these contact line torques can, in some situations, give you azimuthal orientation. And we have gradient elasticity, so these form the basis of liquid crystal science, Frank elasticity. So we have three modes, play, bend, and twist modes. So these are just gradient of Q tensor. Likewise, we have gradient of Q tensor at the surface, as indicated here. For example, this is a biaxial interface joining a uniaxial interface, and at some point, at this point, you nucleate a topological defect. So this kind of energy describes this kind of scenario. And you can envision too that you have gradient elasticity on contact lines, as indicated here, as gradients of Q. These are line gradients, these are surface gradients, and these are 3D gradients. So if you have membranes and surfactants, Lagan interfaces, you can use Helfrich elasticity. So we have Q tensor, right? Now, if you have elastic membranes, you have a B tensor, the curvature tensor. So there is an interesting connection that many people have exploited to a lot of benefit, which is so-called liquid crystal membranology. What is liquid crystal membranology? It's a very specific, systematic way to go from liquid crystal physics to membrane physics on a direct pathway. And the starting point is this identification. The nematic director optic axis can be associated with the membrane unit normal. So this was done first by Helfrich in all his famous work. We have the Helfrich membrane elasticity, which can easily be derived from Frank elasticity. So just take the splay term of Frank and the K24 term that we put for the surface, and you end up with this famous French Helfrich elasticity here put in terms of bending and torsion components. So I have, for example, used this approach to use the so-called polar fluid theory. This is dynamic, viscous theory of membranes. You can show that you can get all the beautiful equations of interfacial transport phenomena, interfacial rheology, using polar fluid theory, and instead of having a director, you say, okay, I forget about the director, I see the director identified with the membrane unit normal, and you get the polar fluid theory mapped into the interfacial rheology equations of Scriven, Boussinesq, Scriven equation plus more physics. So this is an area I think a lot of people are using this approach. And you can also, so you have Helfrich here, B, you can decorate your membranes with rods, for example. So here you have a fiber-loaded elastic membrane. Why you need this kind of objects? For example, The plant cell wall is a biological example. You have pectin, and you have the matrix is elastic, and the cellulose component is a fiber. So what you have is an elastic membrane with a fibrous component. So you have two things. You have a Q tensor to describe the fiber, and you have the B tensor to describe the elasticity, as Helfrich did. So you put it all together, and so this is a simple homogeneous term. So you have two-dimensional orientation here, so you don't have the cubic invariant. So it's Q squared Q4, and so you can now, the only thing you have to do, so this is Helfrich, this is Landau-Degen, and this is what the new physics come about, the coupling. And interesting enough, when you couple B and Q, you have different terms, but the old terms can be put into two bins, two little boxes. One is the curvophilic box that tells you that these fibers seek curvature, and the other is curvophobic that tells you that the fiber escape curvature. The scaling of these coefficients that govern the free energy have different units. That means the ratio depends on a length scale. So we have an internal length scale. C1 over C3 defines an internal length scale. Depends then if you have a big fiber or a small fiber, you can introduce the domination of one effect over the other. So this is, I talk about Thursday, why in plant cells you can have a primary cell walls, first form primary cell wall, and then you start laying matter from outside to inside. So the curvature decreases, the curvature itself, increases because the radius shrinks. You grow inside. So that's why in a plant cell wall, you see a definitive orientation that is in the axial direction during one part of growth, and then perpendicular azimuthal orientation in another part of growth. So this kind of physics too is interesting when you decorate, for example, proteins on viruses. So virus is an elastic shell, and you have to wrap around with proteins. So this wrapping around of objects on smooth, flexible surface, so at some point you can describe it with this kind of BQ type of models. So it's a big area. And lastly, these flexoelectric membranes. So flexoelectric membranes, we couple B and E. So there is something called piezoelectricity, we all know and use it every day. Piezoelectricity is everywhere. So here the comparative or the corresponding effect is flexoelectricity. In piezoelectricity, you create polarization by pressure, by compression, extension, not by shape change. Here we create polarization by shape change. We bend, especially bending. There is no torsion coupling, so it's bending coupling. So here now you do the physics to couple B and E. So this is flexoelectricity. This is, for example, a lipid bilayer. So it's neutral when it's straight. And now you introduce a bending deformation. Here you shrink the area. Here you expand the area. And Petrov did this kind of fundamental work in the 70s, both theoretically and experimentally, and measure polarization upon bending. So this formed the basis of a new kind of coupling between elasticity and electromagnetics, the fact that you can couple B and E. So we have all these energies I described. What's how I'm doing with time? I lost track.
40 minutes.
Huh? 40 minutes?
Yeah.
I better accelerate. Okay, so we have all this proliferation of energies. Sometimes, especially, more kind of people that want to have a clean picture of reality said, oh, you have too many energies, you'll never got anywhere, with all your 6, 8 energies, anchoring elasticity, gradient elasticity, bulk elasticity. It's too complicated. Well, they are organizing principles, First of all, this is a multi-scale and isotropic system. So the simplest flow problem people do, like a simple shear flow, you have 5 viscosities, you know, it's anisotropic. The system is anisotropic. It doesn't have one constant, you know. So we have a proliferation of energies. So if you look at the simplest scenario of a liquid crystal drop, you see you have bulk. I put some numbers here for reference. You have homogeneous elasticity, you have bulk gradient, so this is the Frank constant piconewton, is an important number, Frank constant piconewton. You have, at the interface, you have an isotropic tension. If this is a thermotropic liquid crystal, it's like millinewtons per meter, like organic liquids. On the other hand, if this is, let's say, a liquid crystal drop of a colloidal liquid crystal, a mineral suspension, for example, and this is isotropic phase, this number is very low, and we have ultra low tension surfaces. We also have, this is the key point, the anisotropic component to the surface tension called anchoring. W is the anchoring constant. It obviously depends on the substrate and the liquid crystal. It's all over the map from 10 to the minus 2 to 10 to the plus 2. Depends on the surface, depends on the liquid crystal. These numbers are very difficult to get, and there are very few systems around. The best characterized is systems that are used in the display industry because they form the basis of everything. So anchoring and the gradient elasticity are the key numbers. So when I divide these, and then I have bending and torsion, I can decorate this interface with surfactant, for example, to do shape actuation and other things. So I have a contribution, a Helfrich contribution here. And these drops are multifunctional. They respond to electric field, magnetic fields, they breathe, they do things. So you have all kinds of other phenomena, flexoelectricity, orthoelectricity, dielectric, diamagnetic. So the ratio of these two numbers defines an important length scale, which is the disclination line size, which is 10 nanometers. The ratio of gradient elasticity to anisotropic surface tension is a key number. So it's called extrapolation NEM, is the key number. So L divided by W is the key number. It has units of length because this has units of energy per unit length. So you have an internal length scale in the system, which is called extrapolation length. So the key physics is this. So if you have a liquid crystal drop, or if you embed particles in a liquid crystal of a certain size, R, if the radius of your drop or your particles are bigger than this internal length scale, you have strong anchoring. That means the interfacial shape or the particle size, geometry, penetrates into the fluid. It distorts the fluid. The orientation here is curved. Orientation here is curved. Why? Because you have strong anchoring, strong. On the other hand, if your particles are nanoparticles, very tiny, or you have nano drops of liquid crystals, this size, geometric size, is much smaller than internal length scale. You have weak anchoring, and the particle won't distort the orientation. So this is question number 1, whether you are in the strong anchoring regime or the weak anchoring regime, or you close to a transition. The second point is second example of energy ratio. So I'm talking about different important energy ratios. So one was the gradient elasticity to anchoring. So here, and I talked about homogeneous and gradient energy ratios. So here we look at the ratios between these three quantities. This is the isotropic component of the interfacial tension, this is the anchoring component, and this is the bulk elasticity. So you have three energies and you have two ratios. So these two ratios form the plot or diagram that describes the structure and shape of liquid crystal drops. So many times your drops, they look like this. This is a collagen cholesteric solution. These are collagen drops. This thing is in biphasic equilibrium. So that means the isotropic state and the nematic state are in equilibrium with each other. So these are spheroidal drops of around 50 microns. So this is the diagram, beautiful paper, Prinsen van der Schoot, 2003. You have two axes. One is the ratio of anchoring to isotropic tension. The other one is the ratio of Frank elasticity to isotropic tension. So this diagram gives you an idea of the structure and the shape. So there is a transition line. Above this transition line, the directors are bent by the object. Here we have tangential boundary condition, so you have bending from the size. Below this transition line, the orientation is unperturbed because W is low enough. On the other hand, on this area here, when we are here, we have large drops. So the drops tend to be more spherical, and when we move here, we have smaller and smaller drops, and the shape becomes spindle-like. In addition, the strong anchoring, you decorate the north and south pole with topological defects according to Euler, and this has to be a +2. So you have a +1 in the top, a +1 in the bottom. So you have topological defects decorating when you have strong anchoring, and no defects here because the orientation is homogeneous here. And what is interesting to me anyways is here you have a double kind of singularity. Here you have a singularity in the shape. You have a cusp. This cusp exists here too. Here we have only a geometric singularity. Here you have a disclination line decorating a geometric cusp.
Is it a cusp or is it a corner?
Like a cone. A conical, yeah.
Like still a finite curvature, right? It's a
At
right.
some point, well, if you resolve this with a multi-scale and more defined, at this level, at the macroscopic level, it's going to be a conical structure. So the key point is, at this macroscopic level, you have a cone here, and here you have a cone plus a disclination. Here there is no disclination. And so this is a kind of interesting diagram that summarizes a lot of colloidal liquid crystal systems with these 3 parameters. So yeah, you need the size, right? You need the Frank constant and the isotropic elasticity and the anchoring constant. So for these kind of diagrams, these kind of drops, collagen, if you are in this region here, it's not too distorted, not too far from spherical shape, you end up that this isotropic and anchoring constant, these 2 properties are not too far from each other, and the size parameter R is determined by this point here. So the size of the drop, which is in the several microns, 20 microns for example, is just the ratio of the Frank elastic constant to the isotropic tension. So now we go into, so I talk about order parameters, I talk about energies and energy ratios, so we have a lot of tools under the belt. Now we talk about kind of the balance equations. So out of all these energies, so I have 2 things in the program. One is the balance equation, and the other point is to derive equations for stress and so-called molecular fields. So how the medium distorts this Q-tensor ellipsoid. That's called the molecular field. So these are, I just write them down, the classical equations for nematostatics. There are a couple of new things. So for the bulk, T is the stress tensor. So this is in 3D inside this region. At an interface where I mark these lines, we have the surface divergence of the surface stress tensor is balanced by the bulk jumps across these lines. These brackets denote the jump. Here at the contact line, for example, we augment this, so this is the line divergence of the line stress tensor, and now from the surface, if you use the surface divergence theorem, if you use divergence theorems admitting singularities, you get this cascading. from top to bottom. So that's the net effect of the divergence theorem with singularity. So here, from the surface stress tensor, we have so-called junction sum. These are the junction sum of Young-Neumann equations for contact lines. So this is the Young-Neumann equation that comes from the surface divergence theorem. Now, from here, using the bulk divergence theorem in 3D, with surface singularity, you get this term. With line singularity, you get a so-called pitch-collar force, the junction integral of the bulk stress tensor. So this is the basic equation at a macro level for a contact line. It has the line term, it has the Young-Neumann term, and it has the pitch-collar force. And so the whole point is when these stresses become active, and what do they do? Remember, inside of this, we're going to have anchoring. So the Young-Neumann force is modified by anchoring. And in addition, here we have the pitch-collar force. I'm sorry, I'm missing a C here. The pitch-collar force, it tells you, because we have long-range elasticity, how distortions in the bulk will affect the contact angle. So in addition to the stress equations, we also have the Q-tensor equations. And the Q-tensor equations, they are fabricated by formulating the molecular field. So the minus variational derivative of your free energies in the bulk, in the surface, on the line. So you do systematic study. F here is the free energies for the bulk, the surface, and the line. So you can directly formulate your molecular fields for these three parts. The molecular fields are divided into two important parts. One, the first part is called the Q force. It's the derivative of F with respect to Q. The second part is the Q couple. It's the derivative of F with respect to gradients of Q. And when you do the same formulation using the divergence theorem, then you find for the bulk the molecular field, the symmetric traceless part, because Q tensor is symmetric and traceless. So the symmetrized and made traceless molecular field in 3D is 0. Then using the divergence theorem for the interface, you balance the surface molecular field with the jump couple here. And for the contact line, you balance the line molecular field with the surface junction that comes from the surface here, the surface junction term, and the line contributions from the bulk couple right here. Yeah? You okay? Okay.
So what about Fi? What is Fi?
Sorry?
F sub I. In the first definition, you have A.
Here?
No, yeah, above. First definition.
Here?
There, yeah.
So these are the free energies I discussed.
Oh, free energy. Okay.
Yeah. So these are the free energies I discussed in the beginning for the bulk, the surface, and the line. And they have homogeneous part, they have anchoring part, and they have gradient part.
So when you introduce the energy, do you already select certain phases that you allow, or do we allow for all 50 phases that you mentioned?
No, well, this only orientation, simple fluids, pneumatic fluids. Pneumatic and achiral. Well, at some point we put chirality there, so we'll talk a little bit chirality. So at this stage, we're only in the pneumatic stage of development for this program.
Yeah, but it has the uniaxial and the biaxial.
Yes,
right?
exactly,
Yeah.
automatic.
Okay.
Yeah, and if you want, I find, especially from a computational point of view, I don't know analysis, but from computational point of view, if you work with the Q tensor level, as maybe analysis if you work with a director level and produce a cutoff to avoid singularity, etc. But when you do it numerically, the Q tensor is the simplest and best and most accurate, from my experience and other people I know, is the most accurate and simple, computationally speaking.
If you set P to 0, right, the
Yes.
biaxial, then you would in many systems get wrong results, right? Or
Well, yes, yeah, because as I described, those interface, is the interface, so this kind of system, this system is biaxial. P is different than 0 in this system.
does it mean hydrodynamics is wrong?
Well, no, I'm not saying you're wrong. Well, if you do Q tensor,
Yeah.
well, the simplest case, if you have disks and you put extensional flow, you have a biaxial state. And also, yeah, you have to be very careful because, so you have this thing here, right? So here, this is your nematic fluid. So this is P, this is S, right? This is your nematic fluid. You put in a shear flow, right? You start exciting this root. This root is going to be excited, shear, extensional flow, I don't know. So you got to excite this. And when it's excited, it's not just, if you say it moves in this line, it's uniaxial line, you're restricting all the physics. This is biaxial territory. You excite it, who said it's going to jump in this line? It's going to go most likely, especially with planar flows and compression, etc. This root is excited from this line, and it's not going to just move here.
But let's say standard Ericsson-Leslie theory would just be on this dot, right?
Yeah. Well, yeah, because there is Leslie Ericsson, there's only S.
S equals 1.
S is not part of the equation.
This one.
It's only N.
No, it's not complete, actually.
So the best thing is to go at some level if you want to augment your physics, especially if you want to describe defects, etc. You go from here to here directly. And to go from here to here, yeah, is you advance the physics, but you miss all what I've been talking about. Because, when you nucleate a declination line, you are on this, you are on this line is like this. This is P equal to 3S line. You are here. So you got to go from here to here is all biaxial.
Where is the interaction with the substrate here? This PS,
Yeah,
this is only the only
Yeah.
thing.
yeah,
So,
yeah,
so it is basically it is anchoring.
yeah, exactly. Yes. So all the anchoring is right here. And all the, in here, in the line, we also have line anchoring. Surface anchoring is right here. Because these couples depends on the surface free energy. And the surface free energy has two types of energy. The isotropic part and the anchoring part. So the anchoring is right there. Right here. And then you do the same thing, and you find that this is the equation for the contact line, for the Q tensor at the contact line. Now, the next step is this. What are the relations at the static equilibrium? What are the relations? On the left are all the stress equations, on the right are the Q tensor equations, right? So these are the Q tensor equations, these are the stress equation. This is just the definition of the gradient of the free energy. So if I calculate the gradient of the free energy, and the free energy depends on Q and grad Q, I get this equality. This is just the definition of the gradient of FB, and rewrite it into left side equal to right hand side. And when you do that, you find out that the divergence of the stress is equal to the molecular field double dotted with the transpose of the gradient of Q. It's by definition. So operating the molecular field with grad Q gives you a force. And so when we do that systematically at the bulk level, so this result is for the bulk. This Fi, this should be B, sorry. This is the free energy in the bulk. When you do the same thing, this operation at the surface and at the contact line, we find that this program here. So you have to ask yourself, how many Q-tensor equation and how many force balance equation I have to solve to describe the statics of a liquid crystal drop or contact line. So yeah, the best way is solve all the Q-tensor equation and then solve the following force balance equation. In the bulk, if you know the Q-tensor is at equilibrium, you don't gain any information from the stress tensor equation. It's already included in your solution. Why? Because when you operate with grad Q, H is equal to 0. You operate with grad Q, and you find that you satisfy immediately, directly, the force balance equation of equilibrium. It's finished. When you go to the surface, the program says the number of shape equations is 3 minus D. So in 3D, you solve the Q-tensor equation. In 2D, 3 minus 2 is 1. So that means you solve the Q-tensor equation, and if you want to calculate the size, the shape of a drop, you need to solve the shape equation, right? The capillary Laplace equation for liquid crystals. So this is a little complicated to explain, but it's the same thing. I start with the H S plus whatever. This is equal to 0, right? These are tensors, H equal to 0. So I get the whole thing here. I operate with this object, the transpose of the gradient of Q, the whole equation. I operate with this. And what I find by operating this, this is the Q tensor equation. I operate with grad Q. And what I find when I do a few algebraic steps, I find that when I project that result along the surface, I get this tangential surface balance equation. So that means that the tangential surface balance equation that controls things like Marangoni force, etc., right, that's tangential on the surface, is already included into the Q-tensor equation. And that's a nice result from here, you can see. Basically, we have this couple. Sometimes you need a couple of steps like this. So basically, you have the surface, looks like this, right? That's a molecular field from the surface. And here, this is the bulk coupled. This is the coupled from the bulk. And this is equal to, when I symmetrize, etc., equal to the 0 tensor. Now, I get this equation, and I operate with this guy. If I multiply from the left, I don't have to take the transpose. So you can see that this times this, what is that? That's the bulk stress tensor, sometimes called Ericsson stress tensor. This part, double dotted with a grad Q, is the normal component of the Ericsson stress tensor. So the same reasoning, so that allows you to conclude that for nematostatics, you solve the Q tensor equation, and then you have one equation to describe the shape of your drops. And if you do the same thing for contact lines, you have two equations to describe the shape of a contact line. One equation is for bending of the contact line, and one equation is for torsion of the contact line.
Can I simply see the equation on the surface as sort of a boundary condition for the bulk calculation?
Yeah, yeah. But the whole point I'm trying to kind of get across that you can't just say I'm going to solve all the force balance equation and all the Q tensor equation and crank it up, because there is an inherent dependence that comes from here. It comes from basically like this. It comes from here. This is the definition of the gradient. Well, here I put it in terms of divergence. The divergence of the free energy. It gives you two terms. One is the stress, and the other one is the H field. So they are connected from this definition of the gradient of a function. Okay. So stress tensors. Sorry, it's a little busy, but so we have all these energies. They are all in terms of stress tensors. So the stress tensor depends on the energies you put in the system. The key point is for the bulk, you have a pressure type term that is the free energy, and we have a distortion term, this term here, which sometimes is called the Ericsson stress. So we have a pressure term, diagonal, 1, 1, 2, 2, 3, 3, and you have pressure and shear from Ericsson stress. What is new with surface and lines? Well, yeah, you go here, surface, this is converted into 1, 1 and 2, 2, and this is converted in a 2 by 2 matrix when you have a surface. And in addition, you have anchoring elasticity. So these bulk terms find themselves expressed in terms of tension. This is the free energy. In terms of Ericsson stress in 2D, you have tension and shear. And then you have a new term, which are the bending stresses. So the bending stress is due to anchoring. It's how the anchoring changes with the unit normal. And this gives rise to new stresses, is 1, 3 and 2, 3 stresses. I describe some more later on. So when you do calculate the forces based on these stresses, if you calculate the normal force, this is the capillary force, Laplace pressure force. B is the curvature tensor, right? This exists because you have tension and you have tension and shear. And then you have this new stress. And you can see that the new stress gives you an additional force. And what this tells you is that even if B is 0, you have a flat interface, you can have a capillary pressure, because this term here depends only on the anchoring. So anchoring can support films without curvature. And for the line, it's the same idea. So you have your stress tensor is 1 by 3. You have a tension from your line tensor and your Ericsson stresses. Then you have bending and torsion. Bending is 1, 2 component, torsion is 1, 3 component. You're going to have this bending and torsion because the line tension might have anchoring. You might have preferred orientation. Does a macromolecule want to be parallel to a line or might be perpendicular to a line? So we have tension, bending, and torsion. And again, you can see that lines, you know, this is the normal force to a line. This is the curvature tension. This is the curvature term. This is the line tension. So if you have a line with no anchoring, no distortion, you would have only this term. If you have a string, a piano, guitar string, you pluck it, you activate this term only, right? So you have a taut string, you pull it, that's the tension force. This tells you now, because you have anchoring, you have additional physics, you can distort lines with bending and torsion. So these are some examples of these new stresses. One, this example is orientation Marangoni flow. So Marangoni flow, you have colloidal, thermocapillarity. diffuse or capillarity. You can create interfacial flows with thermal gradients, with concentration gradients. The idea is you generate flows from low energy to high energy. So you put surfactant, you have a surfactant gradient, and you can create a flow. So here we have Marangoni flows due to orientation gradients. So this is observed experimentally. These are distortions on a thin film interface, and these are the scales, spatial scales here are micron range. The amplitudes are small, but very important for beetles and structural column formation. So this is the interface. This is, for example, a cholesteric liquid crystal that is chiral. You have a helix. The helix axis is parallel to the interface. So at each point on the interface, you're going to be sampling different orientation. And because the orientation here, K is fixed, the orientation varies with space periodically, you have a periodical surface tension. Your surface tension varies periodically. When you take the gradient of this along the surface, you generate a force. That force is called Marangoni force. So this is an orientation Marangoni force that creates a material flow. And this material flow from low energy to high energy, because N changes, this changes from 0 to 1 periodically in space, you create this kind of structure without any need of surfactant or temperature gradient, just orientation. So this example here is capillary rise. So it's example how the bulk stresses play a role. So here is a low molar mass liquid crystal. This is capillary. This is the basic experiment, how to compute interfacial tension in a physical chemistry lab. So you put a tube, the liquid goes up. So this term here, the difference of the interfacial tension between the liquid and solid and liquid and vapor or air is called the impregnation. And so this is the impregnation driving force pumping the fluid along this little pipe. And as the fluid level increases, you increase the potential energy, right? So when they balance each other, you get your capillary rise, and you can determine, for example, the interfacial tension. So this is the impregnation, and this is the potential energy. So for a liquid crystal, when the orientation is vertical, you have a longer height than when it's perpendicular. The difference for this 5 millimeter square is 10 millimeters, or is some number. This is an area, you know, we need more data, more experiments, you know. This is at least some data published some years ago that clearly indicate a sensitivity of the capillary rise with respect to anchoring. So when you analyze this problem, you have to put together what happens, what are all the forces acting in the system. So I have bulk forces, I have surface forces, and I have line forces. So the surface force is this integral that involves the bulk stress. And you also have to describe the contact line at the top. So I don't have a lot of time to do very fancy, but basically these stresses acting on the contact line involves the contact line equation. So you plug this equation into here. This term for fluids is 0, and you quickly end up with this equation. Basically, is the system increases the potential energy to a degree that balance this energy decrease. What's new here? Well, what's new is that as this liquid crystal rises going up, you're going to create structure inside the liquid. So there is a new term right there. You're going to create structure because it has orientation. And in addition, you're going to have a decoration of a contact line with topological defects. So this kind of explains or gives a strong reason why this scenario, the liquid rises higher than this scenario. So here, if we analyze the first case, the orientation is perpendicular, you have a square vessel with strong anchoring. That is, the orientation is perpendicular to the surface. And this will create topological defects observed in all kinds of liquid crystals. Why? Because here there is an incongruency at the corners, so you have 4 surface defects, and there is an incongruity in the center. So you decorate each cross-section is going to be decorated by 5 topological defects. In addition, if you look at the surface layer, you're going to have now, you have to deal with defects that might arise along the contact line plus the termination of this central defect. So you have 4 defects on the edges, you have 1 defect in the center. The key effect that the impregnation due to the orientation reduces the impregnation force and increases the energy in the bulk. So this is a minus term. It means as the column rises, you're creating energy in the system. So some of the impregnation force is being wasted in creating the energy. If you compare now the physics to the case where the orientation is tangential, there are no topological defects because the orientation is perpendicular to the cross section. So everything is nice, uniform, there is no gradient elasticity. And so it is, this experiment kind of exemplifies what is the net effect of long-range elasticity to create an increase in the energy in the bulk, as indicated here, by decorating the cross-section with topological defects. And now here we discuss the effect of stress in the bulk, stress in the surface, partial wetting. So we look at the equation of nematostatics, where we have the balance with the line stress, the surface stresses of Young-Neumann, and the junction stress. For typical liquid crystals in glass and polymer substrates, we have contact angle. These are dynamic experiments, advancing and retracting. So, but this number here is close to 20. This number here for polymer close to 50. So these are kind of well-established results. Partial wetting, many liquid crystals on many surfaces, glasses, polymeric surfaces. So here I discuss only static partial wetting case to kind of generalize what we know from the classic equations of capillarity. So you have a pitch collar force and you have a Young-Neumann force as before, but now we have anchoring inside here. So we have 3 different cases observed and discussed in the literature. The first case is strong anchoring. So the anchoring part in the Neumann term doesn't appear, and the only thing, because we have anchoring on the macroscopic long-range scale, we have a pitch collar force. RC is a cutoff force. So now we have an additional term from long-range elasticity through this pitch collar force acting on this point here, and that will affect the macroscopic contact angle. So I'm not taking into account line tension in this discussion. I put it all to 0. So in this case, we have strong anchoring in this surface, strong anchoring in this surface. This case was discussed, for example, by Poniewski and also by myself several times. The other case observed experimentally is weak anchoring. So here there is no anchoring constant here, it's only long range. What about if we have weak anchoring? So this is the case, Lecker-Kircher physical review letters. Here this is a colloidal liquid crystal. So this is meniscus that forms. This is the substrate. This is the colloidal liquid crystal. Here we have a clear different physics. Here we have planar orientation here. We have planar orientation at this isotropic nematic interface. And here we have tangential. And as you move closer and closer to this contact line, now what happens is a new uniform area arises. So here we have uniform orientation. This uniform orientation kind of washes out the pitch collar force because the orientation gradient are 0. So what the only thing that remains is the anchoring terms in this Young Neumann term. So now we have W playing a role right here into this. And there is not a recipe. You have to look at does the pitch color force or the anchoring increase or decrease. It will depend on several factors. One of them, important factor, is whether you have the same type of anchoring in this surface or in this surface, whether the system is symmetric or asymmetric. So we have to look at one case I show you in a minute. And the last case is azimuthal scape. So this is a biopolymer. This is DNA from salmon eggs, experiments 2005. These are more based in droplet evaporation experiments. I agree there is hydrodynamic, there is evaporation, but one key point is we have very nice strong azimuthal orientation. If you accept the fact that you have anchoring, you then accept the fact that you have line anchoring that gives rise to a torque, and this torque now aligns the molecules along the contact line. Therefore, in this problem is isotropic. And so we recover the Young-Neumann equation of contact angles. And this example shows interesting physics for this system, where the contact line equation you can see the effect of the pitch color force when you change the temperature. So these are liquid crystals on a polymer substrate, PBCN. So this is the contact angle and as a function of temperature. So at high temperature, the contact angle is 20. At higher temperature is close to 5. And you have a sharp transition in contact angle driven by temperature. These are similar contact angles with different substrate. And there is no contact angle transition. So here we have a sharp transition, and this transition is intimately related to the fact that at lower temperature, the orientation is perpendicular under steady-state static conditions. At higher temperature, the orientation is tilted. So you have a homotropic to tilting transition around 50. So how you analyze this with our pitch color term? So the pitch color term explains this transition from high contact angle to low contact angle by changing a few degrees. At low T, we have this strong discrepancy between the anchoring at the low surface and at the tilted surface. So to decrease, what the pitch color force does is to increase the angle, to ameliorate this unfavorable condition. At high temperature, if you have tilting and tilting, you can put them together in registry to tilt into the clockwise direction and introduce then a smaller contact angle. So this explains the physics in this problem. So how am I doing with time? I have 3 minutes? Oh, okay. So anyway, so the next point in the program that I wanted to say was these shape equations. But maybe, whether I cut now or I can't just, I better cut off now and discuss it on Thursday. The shape equation. The only point is because we have anchoring, we have capillary pressure that augments Laplace. So Laplace is augmented by what? Is augmented by long-range elasticity and is augmented by anchoring. And the tool, the best tool, which is very elegant and very nice, is so-called Kahn-Hoffman capillary vector. Kahn and Hoffman said for an isotropic system, the interfacial tension is not a scalar. So if you want to do capillarity in anisotropic systems, you have to describe the surface, equip the surface with a vectorial interfacial tension. The normal describes size effects, and the tangential component of that vector describes the tilting. So you can change the energy by changing the surface area or changing the surface tilting. And that gives rise to a new capillary pressure called the Herring's capillary pressure that takes into account tilting. Okay, so I continue then on Thursday.
Yes, just quick question, and the rest, okay.
The capillary rise, I was surprised by the results because I thought, given the condition, the anchoring condition on the free surface as well as on the wall, I would expect the top to be more favorable because that would give you a smaller contact angle. But I suppose that was overridden
Yeah,
at the cost of the defect line.
exactly. So all this is, at this level, the effect, you decorate the bulk with all these massive defect structure. And here there is no defect structure anywhere.
So you really get a larger contact angle in the lower situation.
There is no information on contact angle measurements, I couldn't say, but I tend to, the analysis we did, we got a differential, a significant difference in the contact angle effect, such that this difference, when you calculate the pitch collar force, is more favorable to raise the column in this case than in this case. So basically what I did is I did a full program. So this is just one case where I said at the top surface is perpendicular orientation. So I did the two cases for perpendicular orientation, and also I did the two cases where it's here vertical, here is horizontal, but with the surface is tangential. So out of the four cases, comparing the two pairs, I reached this conclusion. I think this is a beautiful, simple experiment, high school lab experiment, but there is almost no data. I don't know, this is the only data I have, 1999. One paper, one liquid crystal, one capillary. So I think it's a nice, simple area to explore.
Okay, so let's thank Alejandro one more time and break for 15 minutes, coming back at 11:22.